experts call it NPD. Its past has triggered headlines. Its future may change our lives. But behind the history and headlines is a single unrelenting drive. The search for a new source of low-cost electrical power. This is the story of NPD. How do you extract energy from natural uranium and change it to low-cost electricity? This was the challenge faced by Canadian scientists at Chalk River, where there were already some of the world's largest research reactors. The problem? To unlock economically the power in the atom. When an atom is split by nuclear fission, it gives off 2 or 3 neutrons. These, in turn, split other atoms. Each tiny fission creates heat. And as the number of flying neutrons and fissions multiplies, the result is more and more heat. Heat is energy, and the energy generated by a few ounces of uranium is equal to literally tons of coal, oil, or gasoline. What was needed was an economic method of extracting this energy to fill today's needs and to meet future needs as fossil fuels are gradually used up. This was what brought engineers and planners together with Canada's top scientists in order to translate fundamental knowledge into actual practice. The result was NPD, a system whose basic principles can be explained in the simplest terms. First, the reactor vessel, or calandria, a metal tank 15 feet long and 17 feet in diameter. Through this tank run horizontal pressure tubes, about 3 inches in diameter. Uranium fuel is placed inside the pressure tubes. And when heavy water is pumped into the tank, a chain reaction of atom splitting begins in the fuel, which releases very large amounts of heat. Now we have an operating reactor. Pressurized heavy water in a separate circuit flows over the hot fuel and transfers this heat to a heat exchanger. In the heat exchanger, the heat is transferred to ordinary water. The ordinary water is converted into steam in a steam drum. The heavy water circulates back through the reactor to complete the circuit and continue the heat transfer cycle. The steam travels from the steam generator to the turbine, and the turbine drives the generator, which produces electricity. Steam from the turbine passes through a condenser and is returned as water to the steam generator. The reactor is merely a new source of heat. Steam generators, turbines, and electric generators have been used in power plants for many decades. Below the reactor is a dump tank. The reactor is shut down by dumping the heavy water into this tank. During operation, the amount of heat produced is controlled by adjusting the level of the heavy water in the reactor. When the heavy water is raised again into the reactor, the chain reaction begins once more. This is the principle of NPD. To make it a reality, 3 Canadian organizations joined forces in partnership: Atomic Energy of Canada Limited, the Hydroelectric Power Commission of Ontario, and Canadian General Electric. Ahead of these partners lay feasibility studies, the chores of design and development with their thousands of drawings, the careful checking of thousands of calculations by computer and by development work in laboratories and shops, the responsibility of seeing that no problem or detail had been left unchecked. In the spring of 1959, construction work on Canada's nuclear power demonstration began. Its location, the province of Ontario, at a site provided by Ontario Hydro, not far from the Chalk River Research Center. It was soon to become a very busy place. Even as the big steel beams were slicing up rectangles of sky and the first skeleton structure was being hammered into place, other elements of NPD were already underway. Nearly 200 miles away as the whirlybird flies in Peterborough, Ontario, Canadian General Electric was moving in with design and development of the reactor plant and supervising the work of scores of other manufacturing firms. Here was the metal dump tank that would catch the heavy water as the reactor shut down. Here was the fabrication of the uranium fuel. Held in a metal jig, zirconium alloy sheaths were filled with pellets of uranium. While finished fuel elements were being tested for leakage, others were being end welded before they too underwent the exacting tests and inspections necessary for approval. More than 1,000 of these fuel bundles had to be packed and shipped with meticulous care. Here, too, was the calandria, the big metal tank that would contain the nuclear reaction, slowly emerging from its blueprints under the hot glare of welding torches. A big job, and yet for all its bulk, every detail was achieved with extreme precision. Each of the 132 holes for pressure tubes had to be accurate to a few thousandths of an inch. It was a job that would take many months to complete, but step by step, with its thousands of parts and tens of thousands of man-hours, NPD was taking shape. Installation of the heavy water dump tank was a major step. But there was still a long way to go. Supplies continued to flow into the site. Technicians were busy with the installation of turbine and generator. The noise and activity that had been hammering away under the open sky had simply moved inside. With painstaking care, the turbine rotor was slowly eased into its position. The heat exchanger arrived. The steam drum. Inside the reactor hall, welding torches crackled and sparked as the reactor's feeder pipe system was assembled. 2 levels lower down, the reactor chamber itself was double-checked to make sure it was ready for the calandria under construction at Peterborough. It was a busy time in the shops. 4 solid miles of leak-tight aluminum welding was required before the calandria was done. And then one day, it was done. All that remained was to carry it 200 miles. On June 18, 1961, a strange safari moved out of Peterborough along Highway 28. Ponderous with its unwieldy load, it snaked across Ontario. In many places, telephone and power lines hung too low for it to pass. They had to be poled out of the way. One of the bridges along the route was too narrow for the calandria to cross. Its guide rails had to be taken down. In towns and villages along the way, people gathered to watch the strange motorcade. Not many guessed its bulky cargo would one day power industries and heat the kettle for their cup of tea. Installing a nuclear reactor is not a job you can rush. Yet, within a week, the calandria had been maneuvered into place. Its final position, 50 feet below ground level, was right here. When the reactor is operating, all refueling is remotely controlled by automatic machines. Thus, the reactor can refuel without a shutdown. At this stage, there was still need for the human hand and eye, aided by precision tools. The pressure tubes had to be located, and end fittings attached to both ends of the 132 tubes. Each fitting had to be leveled and bolted into position with extreme care. These were the links between the fueling machines and the pressure tubes into which they would feed uranium fuel. After startup, guided by its electronic brain, the fueling machine must lock onto the fitting with near absolute precision. Beyond the problems of installation loomed still another challenge: Ontario Hydro's responsibility for operating the completed station. A special school had to be set up to train picked men, each carefully selected for technical background and aptitude. Nucleus of this team was a small number of men with many years of experience with nuclear reactors and thermal power plants. But the safety and success of NPD would rest with all of them. For many weeks, the training and testing at NPD went on. As they checked every item of equipment, engineers, technicians, and maintenance men slowly grew into an operating crew. They moved easily and naturally in their intricate world of control panels and consoles. Whatever the complexities that lay behind this imposing assembly of machines, they became secondary now to the practice and practicalities of smooth operation. The objective was simple and unchanged: to reach into the heart of the atom and to extract and use its latent energy. This was the system they would take on its trial run: reactor, steam generator, turbine, electric generator, all of them checked and ready to go. Uranium fuel would be placed in the reactor. The heavy water moderator would be introduced, and the chain reaction would begin, generating heat which would be carried away to the steam generator. Here, the heat would be transferred to ordinary water, the ordinary water converted to steam, while the heavy water would circulate back through the reactor to complete the circuit and continue the heat transfer cycle. Thus, ordinary steam would cause the turbine to spin, driving the generator to produce electricity. This was the system that would take energy from the fissioning of atoms and transform it step by step into electrical power for the homes and farms and industries of Canada. They had been through it in theory dozens of times. All that remained was to try the system under actual conditions. To start the fueling operation, fuel bundles are moved from their storage racks and carefully cleaned with compressed air. 1,188 of these fuel bundles are required to load the reactor. However, once the reactor is operating, only one new fuel bundle is required each day. Each bundle is placed in a loading port to be transferred through the shielding wall and picked up by a fueling machine on the other side. Here is a schematic view of the operation. Behind the shielding wall, the operator loads the fuel bundle into the loading port, where it passes through the shielding wall to the fueling machine. The shielding gates open, and the fueling machine descends to the reactor. Here, it rotates through 90 degrees to lock onto the reactor and insert the fresh fuel. Now let's see the actual operation. Here, the fueling machine is moving in to pick up fuel from the port in answer to instructions which are preset by the operator. Once the operator has told the machine his requirement, all refueling steps are carried out automatically. The fuel bundle is taken from the loading port. The heavy shielding gates open. Now, with the control panel continuing to signal each step, the fueling machine descends on telescopic tubes toward the reactor. Automatically, it will search out the first pressure tube which the operator has indicated. When the machine has rotated into the correct azimuth position, it moves along the X, or horizontal axis, to line up with the correct row of tubes. Now it moves along the Y, or vertical axis, to locate the particular pressure tube the operator has selected for refueling. The pressure tube is located. The fueling machine moves in toward the end fitting with its sealing plug. Locks on and removes the sealing plug. As the fresh fuel bundle is fed into the reactor, it pushes out the spent fuel bundle at the other end. The spent fuel bundle is picked up by the other fueling machine and carried away for disposal. On April 11, 1962, NPD went critical. This is simply the scientists' way of saying the fuel first released its energy.
We are ready to start up. Turn in your keys, please. We are ready to start up. Turn in your keys, please.
A carefully designed safety system ensures that the reactor cannot be started up until all keys are accounted for. Only when all keys have been inserted here can the master key be removed for startup. Before he pushes the final button, the operator must prepare the protective system for startup by going through a series of routine startup checks. Now he moves to another set of controls where he adjusts the system which will regulate the power run-up. And now he's ready for action.
The moderator level is now being raised.
During low power operation, tests are carried out on the automatic safety system.
The reactor is being raised to 80 kilowatts. The reactor is being raised to 80 kilowatts.
In the flow monitoring room, instruments indicate whether the flow is operating within its preset limits. Similar limits are set for temperature of coolant, rate of change of coolant temperature, and reactor period. All this data is constantly recorded electronically. If any one of the variables exceeds the limit, the reactor automatically shuts down. The fail-safe dump valves operate. In 15 seconds, the heavy water is drained into the dump tank and the reactor is safely shut down. When the cause of the shutdown has been remedied and the reactor is again ready for operation, the heavy water is raised and power is resumed. Monitors are constantly at work checking for radioactivity in the coolant system. When spent fuel is removed by the second fueling machine, it is discharged down a special chute through the shielding wall into the spent fuel bay. Here, an operator maneuvers it underwater into a container, and after some of the radioactivity has died down, it is shipped to a storage area. Only 2.5 months after first going critical, the NPD station successfully passed its tests and was brought up to its full rated power of 20,000 kilowatts. The launching of NPD in 1962 was only a beginning. Increasingly, the effects of this challenging project will fan out across the country. More and more, nuclear power will contribute to our increasing standard of living, not only along the expanding frontier, but in Canada's busy manufacturing centers. A full-scale nuclear power station was begun at Douglas Point, Ontario in 1961, built by Atomic Energy of Canada Limited in cooperation with Ontario Hydro. It will be operated as part of the Ontario Hydro system. The new station uses the same principle as NPD, but its 200,000 kilowatt power output marks the beginning of a new era, an indication of Canada's progress in the nuclear age. Today at NPD, the roar of the bulldozer has disappeared. Workmen and engineers who built it have moved on to new projects. The station hums quietly among the Laurentian hills. Inside, the small staff goes about its job as though producing nuclear power were a matter of routine. And after all, why not? This was the purpose of NPD, to extract energy from uranium and make it available as electrical power at the simple turn of a switch.